Welcome everyone. Today we'll be solving problem 2 of Project Euler in Python. We'll be solving it with two approaches, one with Python generators and the other with a memoized recursive implementation. So let's first check out the question. So each new term in the Fibonacci sequence is generated by adding the previous two terms. For example, 3 is a summation of 2 and 1, 5 is a summation of 2 and 3, so on and so forth. By considering terms in the Fib sequence whose value do not exceed 4 million, find the sum of the even value terms. So let's copy this. Here we have an empty Jupyter notebook. We're supposed to find the sum of the even value terms in the Fib sequence. Value terms in this Fib sequence, the values of which is less than or equal to 4 million. First, let's go over the generator style implementation. So for that, we'll first define a generator called FibGen. Term 1 being 0, term 2 being 1. While true, we will have to generate the next term. The next term will be equal to the summation of the previous two terms. Then we reassign T1 and T2 to T2 and next term, respectively. So T1 will be reassigned to T2, T2 will be reassigned to next term. Finally, we yield next term. The difference between a function and a generator in Python is that the keyword you use at the very end would be yield instead of return for generators. Now, we can declare a variable called fibs, which is essentially our Fibonacci generator. Let's see if it works. Just print a bunch of fibs. Very nice. What we can do now is we can actually try to solve the problem. We'll use a while loop for that. So within each iteration of the while loop, we will be generating a new term of the Fibonacci sequence. So next term is equal to next of fibs. If the next term is greater than 4 million, then we break the while loop. If the next term is divisible by 2, meaning if next term modulo 2 equal to 0, we will increment some form of some variable. Declare it right here, set it to 0. Finally, we will return s. Let's see if that works. 4613732. Now, let's move on to the recursive implementation. It should be noted that there is actually a very natural recursive definition for the Fibonacci sequence, that being fibn is equal to fibn minus 2 plus fibn minus 1. Because each new term of the Fibonacci sequence is made up of the summation of the previous two terms. Let's formalize this into a function. Fibn minus 2 plus fibn minus 1. Very cool. So, if we simply run this function right now, it will run on indefinitely because we have not defined any kinds of stopping conditions. For the purpose of this question, we will write the stopping condition as such. If n is equal to or less than 2, we'll return n. So let's see if this actually works. For I in range 110, print fib of I. 1, 2, 3, 5, 8, 13. 1, 2, 3, 5, 8, 13. So for the Fibonacci sequence as defined in this problem, we have a correct implementation. However, this current implementation of Fibonacci is actually extremely computationally inefficient. For example, if we run fib 100, it will just keep running. We will have to interrupt it manually. This is due to the fact that in order to calculate fib 100, we will have to calculate fib 98, fib 96. We will have to expand on all terms of the previous calculations in order to get to fib 100. So this is a natural segue to the concept of memoization, whereby we make use of some sort of lookup table to cache the results of previous computations so as to avoid redundant computations. So let's just write a memoized version of Fibonacci. For that, we'll be using Python decorators. So let's define a function called memo, which takes in an argument, which is a function. Let's first define a cache, which is a dictionary in Python, and a set of keys, which is a set. Let's define a wrapped function, which essentially will be the new version of Fibonacci. So the new version of Fibonacci will take in an input of n. If n has already been calculated, so if n is in the set of keys, so if n in keys, we will just simply return the value of cache at key n. Yep. However, if n has not been calculated before, we will have to add n to keys. We will have to declare a result, so value would then be equal to the function of n. So we will just call Fibonacci on n. Then we will save the result to cache. So cache n will be equal to value. Ultimately, we return the value. For the memo function, we just return wrapped func as a function. So here we can make use of our newly declared decorator. So let's see if our new implementation of Fibonacci works. Let's go fib1000, and it does work. There you have it. Next, let's put this function to the test. So let's try solving this problem again. So while true, next term will be equal to fib I. Let's define I first. I would be equal to 1. Let's also define a sum variable, declare it and set it to 0. If the next term is greater than 4 million, then we break the while loop. If the next term is an even number, then we increment the sum variable by next term. At the end of every iteration, we increment I by 1. So let's see if we get the same answer as above. 4613732. Correct. So today we solved problem 2 of Project Euler with 2 different methods in Python. The first one being a generator style implementation, and the second one being a recursive memoized function. Hope that was somewhat interesting. Stay tuned for more content. Thanks for watching.